In this video, we're going to be learning about dilations. Dilations are often referred to as either a reduction or an enlargement. Dilations are non-rigid transformations that maintain the shape of a preimage, but not the size. And the size of the preimage is changed by a scale factor, which we use the letter K to refer to. So there's also always a center of dilation. Just like with rotations, there's a center of rotation. In Math 2, we're going to have the center of dilation be the origin, or the coordinate 0, 0, but the center of dilation can actually be any point on the coordinate plane. There are two main types of dilations. The first is called a contraction, which is also known as a reduction. And a reduction occurs when the scale factor is between 0 and 1. Notice that the scale factor is between 0 and 1, and it is not allowed to be 0, and it's not allowed to be 1. The other type of dilation is called an expansion, which is also known as an enlargement. Expansions occur when the scale factor is greater than 1. So if you think about that, a contraction or a reduction means that your figure is getting smaller, and so that should make sense to you because you're multiplying by a number that's between 0 and 1. And if you want to make a figure bigger, you should multiply it by a scale factor greater than 1. So we just need to understand why k can't be 0 and why k can't be 1. Well, for a scale factor, remember you're multiplying your x and y values by that same number. So if you have your preimage coordinates and your mapping rule is xy goes to 0x, 0y, well, yes, we're technically multiplying, but if you do anything times 0, it's going to be 0. So then you would have a figure and all of its coordinates would be mapped to the origin, and that just doesn't really make any sense. On the other hand, if you have a mapping rule where your scale factor was 1, you would just be left with xy goes to xy, and that's not a reduction or an enlargement. It's just like mapping to the same figure. So that's why we focus on scale factors that are between 0 and 1 or greater than 1. Also note that if your scale factor appears to be negative, that actually means that there's going to be a rotation. So if you had something like negative 1x and then negative 1y, like right up here, this is actually the rule for rotating 180 degrees. So the negatives would actually make your figure rotate. And if you had another number in here like 2, then the 2 would be the scale factor, and the negative would be what would be rotating the figure. So you'd actually have a dilation occurring and a rotation. So again, we really focus on scale factors being a positive number. So mapping rules for dilations, we're just going to show the scale factor in there. So we have xy goes to kx, ky. Remember that k is your scale factor, and for a dilation to occur, you have to multiply x and y by the same number. So the function rule for that would be basically the same thing. You would have f of xy equals kx, ky. K is the scale factor, and it must be the same for both x and y. I can't stress how important that is. Because dilations keep the same shape, but they change size, they create similar figures. And this occurs because x and y are being multiplied by the same number, called the scale factor. Similar figures are figures with congruent angles and proportional side lengths. So all the distances change in the same proportion based on k. So if you look at the top right, we have an example. The purple figure is the preimage, and the blue figure is the image. I can tell this because the blue figure is the one that has the little prime markings, and then the purple image is the one without prime markings. So that's how we can differentiate between preimage and image. So if you look at this, you can tell that they have the same shape. They're both rectangles, and it's easy to see that they're different size. So that's a way to see that these are similar figures. So if you notice, we said similar figures are figures with congruent angles. Well, if you look here, it looks like they all have these 90-degree angles, right? And so those are congruent. It's important to note that congruent angles doesn't mean that every single angle in the shape has the exact same angle measure. It just so happens that with rectangles, we know they all have 90 degrees. But to clarify, if you had something like a triangle that's mapped to another triangle, so notice it got a little bit smaller. If this angle was 30 degrees, then this angle would also be 30 degrees. It doesn't mean that all 3 of these angles are 30 degrees. Okay, so that's really important to note. So we see how the congruent angles are shown in this figure, but we also need to understand how the sides are proportional. So if you notice, if you look at EH, right here, this line segment, we can find out how long that is. It's pretty easy since it's a horizontal line. We can just count. So you have 1, 2, 3, 4. So it's 4 units long. Okay, so then we can consider the line segment E prime, H prime. So if you look here, it looks like it's only 2 units long. So we went from a line segment that had a length of 4 to a line segment with a length of 2, which makes sense because we can see that our rectangle got smaller, so it was a reduction. So we went from 4 to 2. So that sounds like our scale factor is 1/2. And because your scale factor is 1/2, this side length, E prime H prime, is half as long as the original EH. And the same is true for E prime F prime. Notice how it's half as long as line segment EF. And so that's what the proportional side lengths means. And it's really important to see that it's related to the scale factor. There's something else really special about dilations. So the lines that connect the pre-image points to their corresponding image points pass through the center of dilation. And the center of dilation is often called the vanishing point in art. So if you look at this top right picture, the one without the grid lines, you can see what it's talking about because you have your pre-image coordinate A and then its image coordinate A prime. So that's what we're talking about with corresponding image points. It's the ones that like map with each other, right? So if you just connected these two and you extended this line, you can see that it's passing through point O. And in this case, point O is your center of dilation. And this is really shown if you connect it for all 3 of these corresponding pairs of points. So you go B to B prime, it also passes through that point. And then C to C prime is also that point. So this is what it's talking about. In art, it's called the vanishing point. So if you were to draw like train tracks and you want to find the spot where you can no longer see the train tracks, they often use this in art. So we want to look at this other example in the bottom right, and we're just going to demonstrate this property again. So I'm going to look at C to C prime, and I'm going to connect those two. And this is going to be a rough sketch. So if I just extend this line and do the same for B to B prime, notice they're both passing through the origin. And the center of dilation is the origin for this case. So again, you can see that they're all passing through. So that's something really special. And this is actually a really effective way to see if you plotted your pre-image and your image points correctly when dilating, because you can just do that quick sketch, right, and see if they pass through the center of dilation, which again is the origin for Math 2. And if they do pass through the origin, then you probably graphed correctly. But if they don't pass through the origin, you did something wrong. And so that'll be a good way to check your work. So I made a typo on this slide. You can actually consider example 2 for what we're talking about. We just haven't gotten to example 2 yet. So the last few properties of dilations are that all the distances change in the same proportion based on K, the scale factor. They also maintain shape, angle measures, betweenness, collinearity, parallelism, and orientation. Orientation refers to the arrangement of points relative to one another after a transformation has occurred. It can also be thought of as the order of the points when traveling around a geometric figure. So if you look at this top right figure, looking at the pre-image triangle ABC, and we often go around alphabetically when possible. So if I go from A to B to C, notice how we're traveling counterclockwise. Right, so we're traveling counterclockwise. So since it was a dilation and orientation is maintained, when I look at my image, I should be able to travel around counterclockwise as well, around those same points, right? So the only isometry that does not preserve orientation are reflections. So we know that dilations, a type of non-rigid transformation, they do maintain orientation. And we'll also learn that translations and rotations preserve orientation, but the only rigid transformation that does not preserve orientation are reflections. Now we'll do 2 practice problems. For example 1, we're just supposed to look at the mapping rule that's provided and figure out if it represents a dilation and explain why or why not. So looking here, we have xy goes to 2x, 1/2 y. So I noticed that we're multiplying x and y, which is good, right? To do a dilation, we have to multiply. But I noticed that here we're multiplying by 2, and here we're multiplying by 1/2. So in this case, this is not a dilation because we're not multiplying x and y by the same scale factor. And we know for a dilation to occur, x and y have to be multiplied by the same scale factor. However, it is important to note that because we're multiplying, this mapping rule would represent some type of non-rigid transformation because the size will definitely be changed, right? And so multiplying, that affects the size of a figure. It just doesn't create similar figures because the scale factor is not the same. For example 2, we're given the scale factor is 2/3, and then we're given the coordinates for a triangle SMH. We are supposed to graph its preimage and image. So to do this, I find it helpful to come up with the rule. So the mapping rule would be xy goes to 2/3 x, 2/3 y. And we know to do this because it gives us our scale factor. If we wanted to write the function rule, it would be the same thing, but we would just use a different notation. And that would be f of x, y equals 2/3 x, 2/3 y. So to graph this, the easiest way would just be to consider each point separately, right? So we have s 0, 3, and it's going to go to 2/3 x, 2/3 y. So if we have x is 0, 2/3 times 0 is 0, and then 2/3 times 3 is 2. So s prime is at 0, 2. M prime, we're going to have 2/3 times 2, which is 4/3, and we're going to have 2/3 times 4, which is 8/3. And finally, we have h prime. H prime, we're going to have 1 times 2/3, right? So that's 2/3. And then we're going to have -6 times 2/3, which is -4. So our next step is just to plot these points, as well as the points for the preimage. Note that it's really important to get into the habit of considering if we should expect the image to be bigger or smaller based on the scale factor. So because our scale factor is 2/3, I'm expecting our image to be smaller than our preimage. Okay, so over here, all of our tick marks are 1/3. So each black mark that you see written on here represents a value of 1 or 2 or 3. So they're going to be your whole numbers. So S is located at 0, 3. So I'm going to go up for the black tick marks that I drew. I have 1, 2, 3. So this is where S is going to be located. Make sure you plot your point and you label it. We know that M is located at 2, 4. So we have 2, 2, 4 right here. And H is located at 1, -6. And as you can see, I didn't leave enough space on here for the actual value of -6. So we're going to say that this down here is 5, and at the very bottom of the screen is -6. So make sure when you're graphing, you plan accordingly. Okay, so we're going to make this down here H. So before we plot our image, we're just going to connect the points for our pre-image triangle. If it's really important to you to have like super straight lines, you can always use a ruler, but what matters is that you plot correctly, and if it's a little shaky, it's not the end of the world. Now all we have to do is plot our image coordinates. So we found that S prime was located at 0, 2. M prime is located at 4/3, 8/3, and remember that each of the tick marks on this graph are worth 1/3. And H prime is at 2/3, -4. So we learned today that the sides are proportional, right? So you can see how like S prime, M prime, that side, looks like it really is about 2/3 the length of SM. And so we can see that relationship happening. Also remember how we guessed that our image was going to be smaller than our preimage? Well, we were correct. We also know how the lines connecting our preimage and our image coordinates passes through the center of dilation, so we can try to sketch that and notice it should be passing through the origin. And you can do this in your mind if you just wanted to do a quick check to see if you were correct, but I'm just going to try to show you here. And notice how it's just a rough sketch, but it really does pass through our center of dilation. So that's it for our notes today. You need to answer the following 2 questions in the check-in for dilations. Question 1, you have to figure out the scale factor for the mapping rule. Question 2, you have several statements, and you have to select which ones are true concerning dilations. So this lesson was all about dilations, and our learning targets for today are that you can perform a coordinate dilation and express the dilation with a graph, mapping rule, written description, and function notation. You also can describe properties of transformations in terms of angles, circles, perpendicular lines, parallel lines, congruent line segments, proportional line segments, and lines. Please note that this learning target encompasses several other lessons as well, so although you may not have hit every single part of Learning Target 1.8, you hit at least a couple. Shout out to Slides Carnival for letting us have this presentation, and also I want to give credits to Regents Prep for a few of the example pictures I used. All right, thanks for watching.